This is a lecture on calculating the t-score, deciding, and concluding in the paired samples t-test. So calculating the t-score, the formula for the t-score is unchanged. It's the same as the z-score, the same as the one sample t-test, and it is simply t equals sample mean minus center divided by spread. And center and spread are referring to those numbers that we identified in step 2. The sample mean is what we calculate the t-score in a later step. So that is the formula for the t-score. In this case, the sample mean is mdiff, the center is mu diff, and spread is the standard deviation for the distribution of means estimated. And so an example of how this would work, if we have an example with mdiff equals 32.3 and sm equals 12.6172, then t equals 32.3 mdiff minus 0, which is mu, and every time in the paired samples t-test divided by 12.6172, which equals a t-score of 2.56. So the mechanisms for deciding also remain unchanged. So we'll use an example of a two-tailed test that we just used in the past example with df equals 12 and alpha is 0.05, and the sample t-score is 2.56. So first we look up the cutoff point, which is T alpha, which is the same as the t-score associated with alpha, or the t-score for a significance level of 0.05, however you think about it. But the idea there is that we're just taking the t-score associated with whatever we have found in the problem as the significance level, or alpha. And in this case, I went ahead and looked it up, and T alpha is plus or minus 2.18. So let's mark that on here. Plus 2.18 is going to be here between the 2 and the 3. Maybe I'll put it approximately here. And minus 2.18 is going to be between the negative 2 and the negative 3. And I'll place it right here. And as always, we want to shade the tails of the distribution. So always further out than the cutoff point. So in this case, I'll shade in yellow the right tail and the left tail because we're doing a two-tailed test. And we know then that any score that lies in the shaded region is going to allow us to reject. And what are we rejecting? We're rejecting the null hypothesis. And the same over here, this is the reject region. So if we find a sample score that falls in this reject region, we reject HO, and any score falling in this unshaded region, we fail to reject the null hypothesis. So continuing on, we then plot the cutoff point or points on a distribution, which we've just done. We shade the extreme regions, which we've done, and next we mark the sample t-score. So in this case, our sample t-score is 2.56. And so I can see here that T alpha, whoops, let me get my black out for another moment here. T alpha is 2.18, and T alpha is also negative 2.18. And I can see that my sample t-score from calculated earlier is 2.56, which is going to be a little further out than the 2.18. So I'm going to mark it right about here. T equals 2.56. And so now we reject the null hypothesis if T is in the shaded region, which it is. So our decision is going to be to reject the null hypothesis. And that's because our sample t-score is way out here further into the shaded region. So let's take a look and finish up this Rumspringa problem that we've been working with. Does Rumspringa make a difference in young people's level of commitment? And we parsed the problem earlier, so I'm just going to go all the way through to the end. There's the research hypothesis. Young people will have higher levels of commitment after Rumspringa than before Rumspringa. And the null hypothesis that they won't have higher levels of commitment. Now, we went through in an earlier lecture and calculated all this through calculating out the sum of squares, the deviations. So we took each score minus the mean, and we squared it. We figured out the sum of squares, the sum of x diff minus m diff squared. We figured out that the population mu was 0. We calculated the estimated variance by taking the sum of squares and divided by degrees of freedom. We calculated varm by taking the EVAR and divided by n, the number in the sample, and then we estimated the standard deviation for the distribution of means by taking the square root of varm. And when we calculated all that out, we came to the answers on the following slide. And so we described the comparison distribution. This is what we calculated. We moved on to step 3, looking up the cutoff point, and we discovered that the cutoff point in this case, the t-score for alpha, right here, using degree of freedom equals 3, except I think that is a 4 in our sample. Alpha equals 0.05, and one-tailed high equals 2.13. And so the 2.13 gets placed, I'd say, right about here, just above the 2. Maybe that's a little too close, but it doesn't matter as long as we know what that is. And we shade the region in the tail. So we'll shade this region as our reject region. And our fail to reject region is all of the unshaded area. I'll just write the word fail in here. And so now we have done step 3. Step 4, we calculate and plot the sample t-score. So I've done it in writing here, typed up in advance. So I knew that the mean for the sample that we found in the that we calculated much earlier in a previous lecture was 14. We subtracted the 0 and divided by the standard deviation to get a t-score of 2.25. Boy, this looks much like the last problem. Our t-score of 2.25, if we plot it, it's got to be further out than 2.13 because it's bigger. So it's going to be right about here. T equals 2.25. Because it falls into the reject region, we make the decision to reject the null hypothesis. And the conclusion you'll find is a little different because it can be awkward to write it in this particular test. So I'm recommending that you try and be as clear and as possible in your language. So in this case, I wrote, teens who experience the Rumspringa period have significantly higher commitment levels after than before the time away. I'm hoping that's clear. We can't write it quite the same way because it would be so awkward. Like, think about how it would be to actually write population 1 and population 2. It's too abstract. And so we write it this way. We just make it so that it makes sense. We'll get back into our formula in our next chapter. Then we write out our conclusion Our statistic at the end of the conclusion, t with our degrees of freedom here, now not m, you'll notice, equals 2.25. The probability, the p is referring to that alpha, the probability of getting a t-score of 2.25 just by pulling a random group out of this sample is less than 5%.